So as you all know, AI made huge progress in the last few years, and it's setting new expectations from our customers and from us as well. So the big question that everybody is asking is, how can we deliver the same experience on edge device? And can we actually do it? So the good news is 2024, we made a huge progress on small models. Thanks to more trading and better data sets, we can actually get very good results, very close to bigger models, but with much, much smaller models. So the idea of this talk is to try to build an AI assistant, voice assistant for embedded device, and to do this kind of proof of concept to see if we can make it. And using off-the-shelf and easy-to-use open models. Of course, we can discuss whether it makes sense to put voice everywhere, to have a fridge that talks, to talk to your dishwasher, I mean, for sure. But I think it can bring something, some new use case, and can definitely bring something to your products. So let's see a small video to see what we could do.
Illuminate the room.
Light on.
Okay, if that's too bright, turn off the LED.
Light off.
What can you see?
I can see a beer glass.
Okay, and what can you see now?
I can see a coffee mug.
Tell me something about Edge AI.
Edge AI is efficient, private, and works without internet.
Okay, thanks.
You're welcome.
Illuminate the room.
Oops. So you get the idea of this thing that you have no cloud, and you can perform voice recognition. You can talk to your device. You can get meaningful answers, and leveraging the context as well. That you're on the edge, so you actually can see the edge. You can have vision. You can have sensors, and you can use it with very good latency and so on. So that's the idea. But first, we need to bound the problem. And as you all know, we have a lot of constraints with embedded. So we have limited memory, limited connectivity. But those constraints come with nice benefits, like you have privacy, you have better latency. That's very good advantages. And you can, as I was saying, leverage the context. You can get the input from sensors, get the input for video, from the system test as well. And to mitigate the issue with embedded systems that are sometimes lacking CPU, lacking power, you can use a layered approach, like use a very small model at first, which will be very fast, maybe not as accurate, but very fast. And then use a larger model, a bit slower. And at the third line, you can use connectivity and call the cloud. That can make sense as well. I mean, it's not because you can do it without the cloud that if you have connectivity, you'd better use it and make the best use of it. So a basic pipeline would look like this, like speech-to-text, run a language model, and then another model for text-to-speech. If we look at the size and the progress over the last 12 years, where we made huge progress, you can achieve, with similar error rates, 5 times less compute for speech-to-text. You can get similar results with a 13 times smaller model. That's pretty impressive. And I guess it's just the beginning. I mean, it's progressing so fast that what we're saying today in our talks will be obsolete next year for sure. And then we also have DeepSeek that made a huge press coverage earlier this year. The model is so small, but you get results really similar to what you can get with ChatGPT, for instance. That's really redefining what is possible on each device. But the question that we can ask is, what are those benchmarks? Can we actually get the same results from DeepSeek than ChatGPT? How can we compare? It's actually quite complicated to do that, but If we look at some benchmark, we have this one where DeepSeek is actually better than ChatGPT. So we looked into it and to see what does it mean actually. So this is an uncontaminated maths competition. The idea is that, as you know, large language models are using content publicly available to answer, to prepare answers. So if the answer is on the internet, for instance, the LLM can provide the answer. But the idea is to ask questions and problems to which the answer is not available on internet. An example is this problem. I won't ask you the answer. I wouldn't be able to answer myself, but the idea is that you ask that kind of questions to an LLM and see if he can answer and provide all the reasoning behind it. And so, for instance, ChatGPT is not able to answer it, which is actually not very true, because when we made the slide, it was true, but now they fixed it and now we can answer. But you get the idea. I mean, and instead, if you ask DeepSeek, which can run on an edge device, just like the Synaptics Astra SL 1680 here, you get the right answer. It's run on a small embedded device, and it gets it right with all the reasoning. And so that's quite impressive. It actually takes a long time to run. I think it was like 15 minutes or something to provide the answer. But you get the answer. So that's quite a thing. So Cloud 0, Edge 1. But let's try to build something on the edge and see how we can do it. And if we can build something that makes sense and is actually relevant for real products. So for our proof of concept, we can use a Synaptics processor because they are, I think, very perfect for the job. These are MPUs with NPU available. These are all Linux-based solutions. So they are very good for inferencing. And I think the right size for many of the products. You don't need huge power for many applications, and they are really good fit. The SDK is available on GitHub, and you also have SOM and devices available to develop your product today. So they are ready to market. You can prototype it on an Astra board and buy modules and build a real project. And yeah, the Astra kit are available today. So you can order one from a distributor and have it on your desk when you get back from Hardware Pioneer. So let's define requirements. One big requirement for such an application will be contextual knowledge, because base models are very generic. If you ask a base model, what can I put in my dishwasher? You won't have any clue. So we have to enhance the model with data from the manual, from the specification, from the frequently asked questions, and so on, to improve it. This concept is called RAG. I guess many of you are already familiar with it, but yeah, the idea is to provide all this input on top of the question to enhance the results and reducing hallucination. Another big requirement will be speech-to-text time, speech-to-speech time, actually, because we expect an answer to be in a certain time. And so for that, we can use data from studies. And we can see that Japanese are incredibly fast, which is quite shocking. Danish are more relaxed. But the average for English is in the middle, so 236. And we can usually accept that, say that 500 milliseconds is acceptable for a response time. So that's a target that we want to achieve for our product. The question is, can we do it? So in order to answer that, we ran some benchmark on our Astra board. So we took different models, and we tried to see how many tokens we can process per second. And from our results, we can approximate that we can handle about 20 tokens per second. But you may ask, what does token per second mean? So in order to process an input and a query, an LLM will need to tokenize the input. So to transform the, the input in smaller pieces, usually words and so on, which are then encoded as embeddings. And embeddings can be seen as a vector representation of the information. So something that you can then process, that the LLM will be able to process. Same thing on the webback to generate the response. The response is in token, and it has to be de-tokenized back to text. So we can estimate about 40 tokens for a single query. If you add the context, and as I was saying before, if you add contextual data like the temperature in the dishwasher, like, I don't know, this can add up, and you increase the response time because you add more tokens. And as we said before, we can handle only 20 tokens per second. So at this point, we can say that it's not possible. We cannot get something that makes sense to deploy on an embedded system. So we're kind of back to square one. But we'll see if we can find another approach, a faster approach to mitigate those limitations. So the idea here is to use speech-to-text again, but then instead of using directly a large language model, we will actually process the input and tokenize it as embeddings, and then we will compare those embeddings to a pre-generated database of question and answers that can be pre-generated before. And then you output the text, the answer back with the text-to-speech model. With these solutions, you get much better performance because it's much easier to do, much faster, and we are way we can achieve the 500 millisecond target. So the structured data that you could use for that kind of application would be like that. You need to prepare questions and answers. So the idea is that you have embedding of the questions that are generated by our model, and then you compare those embeddings to the pre-generated embeddings for the question and answer, and the one that match the most will be used for an answer and output as an answer. Those Q&A you can generate with a large language model offline. I mean, you can take the manual of your device, you can take information for from your support system for anything, and generate all this question and answer, and hence it. Actually, this model has also some benefits, like it will reduce it will avoid hallucination completely. Because at the end, you don't want your dishwasher to hallucinate. You don't want your oven to overheat because it hallucinates and so on. But it still feels natural. You can talk to the device and get a natural answer from the device. And you can still leverage the context and the system states and so on. That's sorry. That's actually a good way to implement it, to mitigate the limitation from embedded systems. And the key takeaway, I think, from this talk is that embedded systems are quite unique. There is no one-size-fits-all. We have many algorithms available now. It's just a matter of using it, finding a way to combine them, to reuse them, to enhance them. And the possibilities are infinite. Going back to LLM, the LLM are quite amazing. It's incredible what you can do with them, but they are probably not the answer to everything today. Because for embedded device, they are very resource heavy still today, but it might change fast. I mean, the progress made in the last few months is quite incredible. So I'm pretty sure we're gonna see great progress again. And one last thing, a lot of the work on this topic has been benchmarking. You need to define your criteria, define what you actually want to achieve. It's not just about putting AI. it's about benchmarking what you want to achieve. And one last thing, you can build this too. You can, as I was said before, buy a Machina kit. So this is our evaluation platform. You can buy one and reuse all the example on our developer hub. So it's very easy, really easy to use. There is plenty of example. You can redo the same, but you can do really a lot of things. And that's about it. Thank you.